Welcome to the first lecture on conic sections. In the next series of lectures, we will be discussing the properties and equations of many different conic sections like circles, parabolas, ellipses, hyperbolas. So, in this lecture, we will start with circles. So, let us see what a circle means. So, let us say that we have a fixed point O, as can be seen here. So, circle is said to be the set of all points that are at the same distance from a certain fixed point. So, let us say that this fixed distance is r. So, can we find one point? Let us try to find some point which is at a distance r from this fixed point O. So, again when we talk of distance, we are talking of the two dimensional plane. So, we are talking of a surface like this. So, to find a point which is at a distance r from this fixed point, let us first draw a vertical line and a horizontal line which intersect at this fixed point O. Now, to get another point which is at a distance of, let us say, some fixed distance r from this point O, one way is that we consider any straight line passing from this point O. So, let us say let us draw any straight line. So, for example, let us consider this straight line. Which passes from O. Obviously, this straight line is at some angle theta with respect to this horizontal line, and then it is not very difficult to get a point r. So, we can just think of, because if we start at this point O and if we just walk along this line, so we can either go in this direction or this direction. If we go in this direction, so for example, suppose if we move from here to here, then we have covered some distance. So, we can keep on increasing this distance till we reach a certain point, let us say P, which is at that fixed distance r that we initially wanted to have. So, let us say that so starting from O, we go in this direction on this green straight line, and as we move further away from O, the distance between where we are and this fixed point O will increase until we reach a point P such that this distance is r. Now, instead of going in this direction, we could have gone in the other direction, and if we go in the other direction, then obviously we will get some other point. Let us say this point Q. So, this distance is also r. So, now we have 2 points P and Q which are at a distance of r from this fixed point O. Can we find more points like these? Of course, we can find. It is not very difficult, because we can draw another straight line which again passes through O, but at some other angle. Instead of theta, it could be some other angle, right. So, for example, we have this straight line and it is at some other angle with respect to the horizontal line. Again, on this straight line there will definitely exist some point, I can call it, so I will call this P1 Q1 for the first line, and then starting from O, if I go in this direction on the second line, then there will definitely exist some point, let us say P2, such that OP2 is equal to R, and similarly on this side also we will get a point Q2 such that OQ2 is also R. So, now we have 4 points P1, P2, Q1, Q2 which are at the same distance R from this fixed point O. And it turns out that since we can make infinitely many straight lines, because a straight line in this case, so we are only considering those straight lines which are passing through this fixed point O, but there are infinitely many, because we just need to change the angle theta between the horizontal blue line and the straight line that we are drawing. As theta changes continuously, it takes all real values from 0 to 360 degrees, and therefore, corresponding to any possible angle theta between 0 and 360, corresponding to any such angle that we choose, there will exist a straight line. For example, if we take theta equal to 0 degree, then we have this line itself, this horizontal line itself, and on the horizontal line, let us say we have this point P such that OP is equal to R, and this point Q such that OQ is also R. If we take theta equal to 90 degrees, then we are on this vertical line, and then we get, let us say, this point here P3, Q3. So, this is also R, this is also R, and then we can take theta equal to 120, any possible angle. So, since there are infinitely many angles between 0 and 360, what it means is that we have infinitely many points which are at the same distance R from this fixed point O. And now, if I join all these infinitely many points, which I am showing with this dotted blue line over here, so now let us say these are those infinitely many points, right. So, if I just plot all those points and if I connect them, we get our circle. So, in short, a circle is a collection of points which are at a fixed distance from a given fixed point. In this case, the fixed point is O, the fixed distance is R. As an example, the fixed point O here could be the origin in our coordinate system. This point O could be 0, 0, and r could be, in this case, let us say 3.5 units. Also, this fixed point O is called the center of the circle. So, the fixed point O is the center of the circle, and this fixed distance is called the radius of the circle. Now, if we take any 2 points on the circle, so let us say this point here and any other point, let us say this one here, or let us say not that, let us say we take this point and this point. So, we take let us say P4 and Q4, and let us say, so these 2 points are, they belong to the circle, they are on the circle, and we connect them by a line segment. Then such a line segment is called a chord. It's called a chord. So, chord is any line segment joining any two. So, the chord is a line segment joining any 2 points on the circle. So, we do have a special chord where suppose if we, for example, if we take our case, so suppose we take P1 and Q1. So, we say P1 and Q1, both of them, they are on the circle, and therefore, this line segment between Q1 and P1 is a chord, but it is a special chord. It is a special chord because it passes through the center of the circle. Therefore, such a chord is given a special name called as diameter. It is called a diameter. So, in this case P1 Q1 is a diameter. Similarly, P2 Q2 is a diameter also, and as you can see there are infinitely many diameters. Now, what is the length of this diameter, this line segment? If you see any diameter, then it is composed of 2 radius. For example, in the case of P1 Q1, because a diameter passes through the center, this length P1 Q1 is P1O plus OQ1, because P1 Q1 is a straight line, and we know that both P1O and OQ1 are equal to R, and therefore, P1 Q1 is 2 times R. So, from that we see that diameter is always twice the radius. So far we have seen how to precisely define or what we basically mean by a circle. But in maths we have to always express things formally in terms of equations, just as we define the equation of a straight line. So, if we go back to equation of a straight line, so suppose these are our coordinate axis, this point is the origin, and suppose that we have this straight line. So, this straight line is essentially defined by all those. So, how did we formally define this straight line? So, straight line is nothing but the collection of all the points that lie on this straight line. And then we said that, let us say we have any arbitrary point here whose x coordinate will, let us say, x, and whose y coordinate is, let us say, y. So, we have a point P here. Now, then we went to find out, then we went on finding out what property this x and y should satisfy, so that it will lie on this straight line. Now, if we see here, this straight line passes through this point x 0 y 1, which is this point. Further, this angle here is (45°). That is because the slope of this line is 1, and that is very easy to see, because we see that this straight line also passes through this other point here, whose coordinates are x 1 y 2, and therefore, the slope of the line is 2 minus 1. So, y 2 minus y 1 divided by x 2 minus x 1, which is 1. The slope equal to 1 means that the angle between this straight line and the horizontal axis is 45°. Now, since the slope is equal to 1, it now becomes very easy, because if I try to, if we have this point x y, and if it is said that it lies on the straight line, the same straight line, then if I calculate the slope of this line segment between P and 0 1, then the slope of this line segment should also be 1 itself. So, it will be 1 if and only if this point x y belongs on the straight line. Now, the slope of this line segment is y minus 1 divided by x minus 0, and the slope should be 1, because we calculated that the slope of this straight line is equal to 1. So, that is how we get this equation, and then if we simplify it, we get y equal to x plus 1. So, then we say that this straight line is a collection of all those points for which the y coordinate is 1 more than the x coordinate. For example, if somebody gives me a point 6, 8, x is 6, y is 8, I can immediately check whether this point belongs to this straight line or not, because, and one can see that it does not belong, because y is 8 and x plus 1 is 7, and 8 is not 7. So, I just put y equal to 8 and x equal to 6, and I see that this equation is not satisfied by this point, and therefore, this point does not lie on this straight line. And then it is very easy to write down this. So, essentially what we have is a characterization of the entire straight line. So, now for the case of circle, our objective is to get a similar characterization, or basically some kind of a rule like this, which the coordinates of any point on the circle must satisfy. Let us go back and let us say that this is our these are the coordinate axis, x axis, y axis, and suppose we have a circle whose center has coordinates h comma k. So, the x coordinate of the center is h, the y coordinate is k. And let us say that the radius is r. Now, suppose if we say that there is a point P whose coordinates are x and y, and let us say that P lies on the circle having center h k and radius r. Can we now form a rule for which this x and y must satisfy, so that given any point, just like in the case of the straight line, given any point, if we are knowing its coordinates, if we know that this rule, then we should be able to check and tell whether that point is going to lie on the circle or not. So, let us first connect the center with the point P. Now, since the radius is r, the length of this line segment OP will be r. Let us draw a horizontal line passing through the center O. So, obviously, the x axis and this line are parallel now, and we make a vertical line passing through point P. Obviously, this vertical line and the y axis are parallel, and because the x and y axis are at 90 degrees, it is easy to see that this angle is also 90 degree. Let us denote this point of intersection of these two lines which I constructed by Q. So, now what we have is a right angle triangle here. So, we have a right angle triangle OPQ. Now from the Pythagoras theorem, it then follows that OP square is equal to OQ square. OP square is equal to OQ square plus PQ square. But OP square is R square. How much is OQ square? If we see, because the x coordinate of this point P is x, this horizontal distance is x, the x coordinate of the center O is h, therefore this distance is h, and therefore it is easy to see that OQ square will be x minus h the whole square. And similarly, this vertical distance is y, which is the y coordinate of this point P. This vertical distance is k, which is the y coordinate of the center O, and therefore PQ square is y minus k whole square. So this is the rule that we were talking about. So here, just as for the case of straight lines, even in the case of circles, we get a general rule which the coordinates of any point on the circles, which the coordinate of any point on the circle must satisfy. For example, let us say that we have a circle whose center is the point 1, 2, and radius is 5 units. So let us say we have a point x y which is equal to -1, 3, and now we have to check whether this point -1, 3 lies on this circle. So the circle is specified by the center 1, 2 and the radius 5. So it is not very difficult to check. So in this case, this is R, this is H, and this is K, this is X, this is Y. So we just try to put these values here and check if we get an equality. The left hand side of course is 5 square, which is 25. On the right hand side we have x minus h, so -1, -1, which is -2. So -2 square is 4, y minus k, y minus k, 3 minus 2. So, 1 3 minus 2 whole square is 1. So, on the right hand side we have 5, on the left hand side we have 25, and they are not equal. Hence, this point minus 1 comma 3 does not lie on the circle having center at 1 comma 2 and radius 5. This particular form of equation of a circle is called the center radius form, and it is quite clear why we have that name center radius, because just by looking at this expression we see that the center is h comma k and the radius is r, which is on the left hand side. So, for example, if I tell that, so let us consider this equation of some circle in the so this equation is an equation of a circle in the center radius form, and just by looking at it we can very easily say that the center of the circle is 3 comma 7 and the radius is, so this is r square, so r is 8, radius is 8. But this is not the only way of specifying the equation of a circle. There are some other ways. So, one such way is known as the parametric form. So, what we have in the parametric form is that, let us again draw the coordinate axis. This of course is the origin, and suppose we again have a circle with center at h comma k and radius r. So, let us say this is the center h comma k, radius is r. Now, we need to go back to that construction of all the points of on a circle based on drawing a straight line, drawing any straight line passing through the center. Now, if we draw a straight line, let us say this line here, so this line, which of course passes through the center of the circle h comma k, and let this straight line make an angle of theta with the x axis. So, I draw a dotted line here parallel to the x axis, and this straight line makes an angle of theta. So, always measure theta in the anti-clockwise direction. So, if I go like this, I have positive theta. If I go like this, I have negative theta. Let us say that here we have a point P whose x and y coordinates we have to find, or let us say, if you remember the way we found this point P, given this radius r was that we started moving on this straight line in this direction, and we moved until we reached this point P such that OP is equal to R. So, that is how we started finding points on the circle. If we go back to the first or second slide of today's lecture. So, this is R. So, if this is R, and if I also draw a line parallel to the y axis, then it is clear that these two lines constructed by me will meet at some point q over here at an angle of 90 degrees. And then I have this little right angle triangle here OPQ, where we know that OP is equal to R. But because OP is R, from our knowledge on the trigonometric ratios, we know that OQ will be equal to R cos theta, which is here. So, this is R cos theta, and QP will be R sin theta, which is this. Now, from this we should be able to find out the two coordinates of this point here, which lies on the circle. So, now what we are going to do is we are going to express the x and y coordinates of this point P, which lies on the circle, in terms of r and this angle theta, and that is not very difficult because the x coordinate of this point P is equal to this distance. So, let us say that we have P x y. So, the x coordinate is this much, this is x, but this x is nothing but, so in fact this is also x, but this x is nothing but this distance plus this. Therefore, x is this distance is equal to the x coordinate of the center, which is h, plus, and this distance OQ we have already found it to be r cos theta. Similarly, the y coordinate of this point P, which is this distance here, this is y, is nothing but this plus QP, but this is nothing but equal to the y coordinate of the center O, which is k. So, y is equal to this much, which is k, plus QP, but QP is already r sin theta. So, indeed we now have expression for the x and y coordinate of this point P in terms of the coordinates of the center of the circle, the radius r of the circle, and the angle theta between this straight line and the horizontal x axis. But can this be formed into some kind of a rule, just as we had in the center radius formulation? And it is not very difficult. We can define the entire circle to be all those points x and y where x is h plus r cos theta, y is k plus r sin theta. Indeed, if we go back, we can see that x minus h whole square is, so x minus h is r cos theta. The square of that is r square cos square theta. Y minus k is r sin theta. Square of that is r square sin square theta. Now, if we add these two, then what we get is r square cos square theta plus r square sin square theta, which is nothing but r square, and which is nothing but the rule which we just saw now in the, when we were discussing the center radius form. So, if we add these two, we end up getting this, which means that any point P on the circle can firstly be written, the coordinates of any point P on the circle can always be written like this, where theta is some angle between 0 and 2 pi. Further, if for any theta we choose between 0 and 2 pi, 0 to 2 pi, if we form a point having x and y coordinates as h plus r cos theta and the y coordinate as k plus r sin theta, then such a point will obviously lie on the circle, and that is what we proved here. So, with both these arguments, what we can conclude is that the circle is nothing but the set of all points x and y, where the x and the y coordinate are essentially h plus r cos theta and k plus r sin theta, theta belonging to the interval 0 to 2 pi. So, as we, and it is very clear that as we vary theta from 0 to 2 pi, we are essentially moving. So, when theta equal to 0, our point is somewhere here, and then we start moving like this, and then if we further increase theta, we will reach somewhere here. So, if we reach here, then we are basically having theta equal to 90 degrees, because in that case this will be the straight line and this angle will be now 90 degrees, and then we can go beyond theta 90 and then complete an entire revolution. So, when we express the circle in this form, it is in terms of a parameter theta, and therefore, this type of equation of a circle is known as the parametric equation of a circle. So, essentially what we have said is that we have said two things. If a point x comma y belongs to a circle having center hk and radius r, then x must be equal to h plus r cos theta and y must be equal to k plus r sin theta for some theta belonging to 0 to 2 pi. So, there should exist some theta such that x is this and y is k plus r sin theta. So, this is one thing that we have said. The other thing that we have said is that for any angle theta belonging to 0 to 2 pi, the point h plus r cos theta and k plus r sin theta. So, this particular point belongs to the circle having center h comma k and radius r. So, these two things we have shown. If we go back to our center radius form and if we recollect it, it was of this form. But if we open up these squares, we get x square minus 2 hx plus h square plus y square minus 2 ky plus k square equals r square, or x square plus y square minus 2 hx minus 2 ky plus k square plus s square minus r square equals 0. So, starting from the center radius form, we eventually get this, and our claim is that the equation of a circle can in general be written in this type of form, which is x square plus y square. So, the coefficient of both x square and y square will be the same, and that is because that is basically starting from here. And then we will have a term containing x only multiplied with some coefficient. So, here just like we had this term, then another term linear in y. So, this is another term which is y times some constant plus a constant c. In this case, in the case of the center radius form, c is this, 2f is minus 2k, 2g is minus 2h. So, this is the most general form of a circle. This is basically a second degree equation in x and y, but with some special properties that the coefficient of x square and y square are the same, and secondly that there is no term which contains the term, there is no term here which is some constant times x y, because in a general second degree equation, a general second degree equation is of this form: ax square plus by square plus c xy plus 2 dx plus 2e y plus f equals 0. So, this is the form of a general second degree equation, but here if we see the coefficient of x square and y square need not be the same in general, plus this coefficient of x y need not be 0. But if in this general second degree equation, if we have a equal to b and c equal to 0, if these two conditions are satisfied, then what we get is an equation of a circle, because if we put a equal to b and c equal to 0 here, then we'll get ax square plus ay square, because b is a, and then cxy will disappear because c is 0, 2dx plus and if we divide everything by a, we get and this obviously is of the form x square plus y square plus 2gx plus 2fy plus c is 0. So that is why this is the most general form of an equation of a circle. Now, when we have a circle in this form, how do we find the center and radius? Well, we can simplify this. So, we bring these two terms together. Y square and 2fy together, and then we complete this. You put a plus g square and a minus g square. You put a plus f square and a minus f square. So, what we get is x plus g whole square plus y plus f whole square is g square plus f square minus c. And this reminds us of the form of the center radius form, which is x minus h whole square plus y minus k whole square equals r square. Now, this obviously represents a circle only if and only if this right hand is r square. R square is always non-negative, and therefore, this represents a circle if and only if this is non-negative. So, this condition must always hold. If this is negative, if we get an equation of, and if we calculate g square plus f square minus c to be negative, then this is not an equation of a circle. But if it is non-negative, then it is clear that it is an equation of a circle, because this is the same as this over here, in which case the radius is simply, because r square is this, therefore, the radius is square root of g square plus f square minus c, and the center is h comma k, but h is minus g because this and this are equal, and k is minus f. And therefore, we can conclude by saying that a general equation of this form is a circle if and only if d square plus f square minus c is non-negative. In which case the radius of the circle is r equal to square root of d square plus f square minus c. That is from here, because this r square and this term have to be the same. And the center of the circle is, in the center of the circle is minus g comma minus f. That again we can see from here, because g has to be equal to minus h, and therefore h is minus g. Similarly, k has to be minus f. Hence, we conclude this lecture with the understanding of this general form of the equation of a circle, where we saw that this represents a circle if and only if g square plus f square minus c is non-negative, in which case this is the radius of the circle and minus g comma minus f is the center of the circle. So, essentially, if we are given any equation of this form, we should be able to find, first we should be able to check whether it is a circle or not, and then we should be able to find the radius and the center of the circle. So, we will take more on this and other methods, other type of forms of equations of a circle in the next class.